Hello everybody and welcome back to another episode of Maths. In the last video, we extended our fraction abilities and we introduced how to multiply them. We used a visualization from regular multiplication in order to help us appreciate where fraction multiplication comes from, and we saw that for the most part it's pretty much easier than fraction addition. No common denominator necessary, just straight multiplication all the way across. So I've prepared some practice problems for you to get comfortable with this concept. So as always, pause the video, try them out for yourself first, and once you've given that a good honest shot, we'll go through them together. Alright, so the first problem says perform the following multiplications using the geometric visualization in the lecture video. So this is where we kind of set up our little bars and then spread it out over a grid and then counted the amount of squares that we had. So obviously this isn't the most efficient method, but it's very important to know because you actually know why we multiply fractions the way we do. So to start off with, we're going to construct our 1/2 and 2/7. So I'm going to split a whole into two pieces, and we're shading in one of those. So that's our 1/2. And then for the 2/7, we're going to split another whole into 7 pieces. Okay, and we're going to just assume those are all evenly sized, and we're going to shade in 2 of those pieces. Right, because that's going to be 2 out of the 7 that we have in total. And now what we do is we just extend the grid, right? We extend these grid lines. Essentially, we're multiplying them now by doing this. And so the amount of grid lines we get in total, that is us basically doing this 7 times the 2. We're multiplying the denominators. So we would expect 14, since 2 times 7 is 14. But if we count, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, so we get 14. So the 2 times 7 is 14 squares. And then what we do is we shade in the blue pieces, right? So we basically construct a rectangle from these blue parts here, right? So it's a 1x2 rectangle, and there are a total of 2 of those squares shaded in blue. Slap in a fraction bar, and we get 2/14, which we can simplify down into a 7th. Alright, so now let's try this next one, which is a 4th times 5/3. So this is a little more interesting because we actually have an improper fraction. So we'll deal with that in a second. Let's just start with writing 1/4. So we're going to split this into 4 pieces and shade one of them in, so that is a 4th. And then for the 5/3, well, that's an improper fraction, right? So we still have to kind of take a whole and split it up into 3 pieces. But since there's 5 of these pieces, we actually have to do that again with another whole, right? Since 5/3 is greater than 1, right? Filling this up completely will be 1, and then we're going to have a little bit left over. So now when we shade in 5 of these pieces, we're going to get 1, 2, 3, 4, 5, right? And we see that this is the same as 1 and 2/3, right? That's another way to kind of go between improper fractions and mixed numbers. But now, once again, just like before, we're going to extend the grid lines. But we're going to leave this gap here, and we're actually going to extend them over here once again. All right, in each one of these kind of sections, we have 12 squares, right? 4 times 3. And we have to count these separately. So in total, we've got 12 squares kind of in each of these grid sections. So that's 4 times 3 is going to be 12 squares. And then we look at how many are shaded in. Well, once again, we're kind of constructing a rectangle across these by looking at these 5 by that 1. So we have 1, 2, 3, 4, 5. We get 1 times 5, which is 5. So that means the total area here is 5/12. If instead we constructed something like this where we did count all of the squares, there was no gap in between, and we counted all of them, then what we would actually be doing here isn't 1/4 times 5/3. What we'd be doing is we'd be doing 1/4 times 5/6, right? Because now, instead of splitting one up into 3 pieces, we're splitting one up into 6 pieces, right? So this is different, right? Because here we're splitting one up into 3 pieces, but because we have more of those pieces, we have to basically have multiple ones that we split up into those pieces. So there is a difference. And so if we did this one here, this would give us 5/24. So keep that in mind when you're doing this method for improper fractions. And for some extra practice, multiply several fractions using this method until you get a good hang of it. Make sure to not avoid doing improper fractions because, as we saw, there's a bit of a nuance with it. So try that out. All right, question 2 says calculate the following. These are just some straight multiplication problems. So we have 3/5 times 2/5. So multiplication, multiply the numerators, multiply the denominators, and you're done. 3 times 2 is 6, 5 times 5 is 25. Nice and quick, right? Next one we've got is 7/4 times 11/20. 7 times 11, that's 77, and then we multiply the denominators. 4 times 20, that is 80. And we also should be making sure that we're checking to see if we can simplify these at any step. This one, it doesn't look like we can simplify it, but it's always good to just kind of check. And for this third one here, we're doing a negative times a positive. So our answer should be negative. So we'll make sure to add that in afterwards. So we've got negative 2/9 times 5/3. Now, 2 times 5 is 10, and 9 times 3 is 27, and we can add in that negative. Now, there's one kind of important point I would like to mention here. If I have something like negative 2/9, I can also consider this to be negative 2 over 9, or 2 over negative 9. The reason being is that if a number is negative, well, if I construct that number by doing negative 2 divided by 9, I'm doing a negative divided by a positive, I get a negative. Or if I do a positive divided by a negative, I still get a negative, right? So we can actually think of a negative fraction as being either a negative numerator divided by a positive denominator, or a positive numerator divided by a negative denominator. Why am I mentioning this? Well, if we considered negative 2/9 times 5/3, another thing that we could do with this is say, okay, well, this is like negative 2 times 5 over 9 times 3, which would be negative 10 over 27, which is the same thing as negative 10/27. Or we could also view this as 2 times 5, and then put the negative in the denominator as negative 9 times 3. 2 times 5 is 10, negative 9 times 3 is negative 27. But regardless of the way we do it, these are all equal to each other. So that's just kind of one thing that you might see moving forward is sometimes the negative will be in the numerator or in the denominator, but it's the same thing as just the whole fraction being negative. So I just wanted to clarify that here. And looking at the last portion, we've got 10/3 times 10/7 times 10/11. Okay, so this is an interesting one because we've got more than 2, but that's fine. Multiplication, we can multiply as many things as we want, right? So multiplying the numerators, 10 times 10 times 10, that is 1,000, right? We've got 3 zeros here, so we get 1,000 in total. And then 3 times 7 times 11. Okay, so we could maybe do 3 times 7, which is 21 times 11. And let's do that on the side here. All right, and we get 231. So we get 1,000 over 231. Now, how do we know if this is simplified or not? Well, we can know it's simplified because look at the fractions we're starting with. All of these are tens on top, right? And on the bottom, we have 3, 7, and 11. So there are no common factors on the top or bottom, right? The top is going to be comprised of only 2s and 5s if we think about its prime factorization. And 3, 7, and 11 are actually all primes already. So basically our numerators all in terms of 2s and 5s and our denominators all in terms of 3, 7s, and 11s. So we already get it's simplified. And this is an interesting thing with fraction multiplication is because the numbers we start with are usually smaller than the numbers we end with. And if that's the case, then it might be easier to actually look at the numbers we started with in order to determine if our number is simplifiable or not, because the factors present here are the same as the factors present in the number we end with, right? So that's kind of an interesting little point that is actually going to become relevant in question 5. And for some extra practice, just make up your own fractions, right? Both regular fractions and improper fractions, some negative, some positive. Multiply them together, and make sure to do more than just 2 together. Multiply 3, 4, 5, and so on and so forth. Just keep going until you feel comfortable with it. All right, for question 3, we have some more multiplication, but now we have some whole numbers and mixed numbers involved. So maybe there's a little bit more steps to worry about here. So for the first one, we have 5 times 8/3. So how can we do this? Well, what we can do is we can convert 5 into a fraction, which is the same as 5 over 1, and multiply it by 8/3, and now it's just the same as before. 5 times 8 is 40, 1 times 3 is 3, and there is your answer. We also don't necessarily need to do this step of dividing by 1. We can just immediately do the whole number times the numerator because we know that this step is always going to result in the exact same denominator anyways. Part B, we've got 21 over 2 times 10 and 3/5. So the way we deal with mixed numbers for multiplication is we just convert them into improper fractions because we know that's where the multiplication is the easiest. So to do that, we can do 10 and 3/5. We'll do 10 times 5 is 50 plus 3. We get 53 over 5 is our fraction we're dealing with. So this becomes 21 over 2 times 53 over 5. And 21 times 53, let's do that on the side here. So we get 1,113 over 10, and that will be our final answer. If we want, we can convert it into a mixed number, but it had an improper fraction and a mixed number in there, so it's kind of up to us as to what we want to convert it. Let's do the last part. So we've got -2.5 times -5 1/3. So since we're doing a negative times a negative, we know that's going to be positive, so we can actually just ignore those negatives, right? And reduce this problem to be 2.5 times 5 1/3. And we want to convert these into improper fractions. So 2 times 2 is 4, plus 1 is 5, so we get 5 halves here. And then for this one, we have 5 times 3, which is 15, plus 1 is 16 thirds. So this is equal to 5 halves times 16 thirds. Multiplying this out, we get 5 times 16, which is going to be 80, and 2 times 3, which is going to be 6. But this can be reduced. 80 and 6 are both divisible by 2, so we end up getting 40 thirds as our answer. But since we started with mixed numbers, it makes sense to put our answer as a mixed number as well. So let's convert 40 thirds into a mixed number. And we end up getting 13 and 1/3 as the final answer there. And if you want some extra practice, multiply some various fractions, but make sure you multiply them with mixed numbers and whole numbers this time as well. Make some negative, and sometimes do more than 2, right? You could do 3 mixed numbers or 7 mixed numbers, right? So spice it up a little bit, and let's go on to the next question. 6 quarters, 5 dimes, and 2 nickels. Use fraction multiplication to show how much money I have. All right, so what we need to do here is we know that this is something we could have done from the previous unit by just saying, okay, this is the same thing as 6 over 4, 5 over 10, and 2 over 20. But as we talked about in the last video, there's another way to kind of think about this in terms of fraction multiplication. Having 6 quarters, we know the value of a quarter is 1 over 4, and having 6 of them is the same as doing 6 times 1 over 4, right? So our 6 quarters, that is the same as 6 times 1 over 4, or 6 over 4, which can be reduced to 3 halves, right? So ultimately it's the same thing, but we're just making sure that we understand that this can be written as multiplication. 5 dimes, well, we're taking 5, and the value of a dime is 1/10 of a dollar, right? So we're doing 5 times 1/10, which is 5 over 10, which is a half. All right, and then we're looking at 2 nickels. So once again, this is 2 times whatever the value of a nickel is, which is 1/20th of a dollar, right? There's 20 nickels in $1. So doing 2 times 1/20th, we get 2 over 20. 2 over 20 is 1/10. Okay, so now what we're doing is just adding these up, right? 3 halves plus 1 half plus 1/10. So now this is going to be a little bit of a review from fraction addition. 3 halves plus 1 half, that's a common denominator, so we can just add those to get 4 over 2 plus 1/10. And 4 over 2, that is just 2 plus 1/10. Since money is usually expressed in terms of dollars and cents, it actually makes more sense to convert this 1/10 into a decimal, right? So 1/10 as a decimal is 0.1. So what we end up getting is 2.1, or $2.10. All right, let's move on to the last question. All right, so the first question says, give an example to demonstrate that the product of 2 simplified fractions won't always be simplified. Now, this might surprise some people at first because they might think that 2 simplified fractions, when we multiply them together, should also give us a simplified one. For example, 1/3 times 1/2, right? That equals, well, 1 times 1 is 1, 3 times 2 is 6. Hey, we get a simplified fraction. These were 2 simplified fractions to begin with, so boom, we get a simplified fraction. But this is the danger with making generalizations from examples, because just because it works for this example doesn't mean it's true in every single case. For example, if I do 2/3 times 1/2, these are both simplified fractions, right? What I end up getting is, well, we get 2 times 1 on top, which is 2, and 3 times 2 in the bottom, which is 6. But 2 6s is not simplified, right? This can be reduced to 1/3. So we see here that basically we don't get a simplified fraction right off the bat when we multiply two simplified fractions all the time. So this is an example that wouldn't work, and there's infinite examples, right? But basically the idea is, the way I constructed this is ultimately what we're going to end up doing is we're going to be multiplying these anyways, right? So all the factors that we get up here will be interacting with all the factors down here. And so the way I constructed this was I noted that, okay, if I put a 2 here, even though there's nothing with a factor of 2 here, I can make something in the denominator over here that's going to have a factor of 2. And by doing that, the product's going to have a factor of 2, which means that these are going to have a common factor of that 2, which is exactly what they had, right? And that's what simplified this fraction down by dividing the numerator and denominator both by 2. So for another example, let's say I had something like 5/7. Okay, yep, that is coprime. All I need to do now is get a numerator that has a factor of a 7, because then the fraction will be able to be reduced by that factor of 7, or get a denominator that's a factor of 5, because once again, the numerator and denominator in this resulting fraction will be divisible by 5. So for example, I could do 14/3, right? So this is another simplified fraction, but when I multiply these out, 5 times 14 is 70, 7 times 3 is 21. 70 and 21 are both divisible by 7, and we can just simplify that right down into 10/3, right? So we didn't get a simplified fraction because this and this both carried a common factor. All right, so try some more examples other than what I have here, and just really think about why is it not necessarily giving me a simplified fraction. All right, and now let's go on to part B, which says, what are the conditions two fractions must meet for their product to be simplified? So this is kind of like what we were just talking about. The reason this didn't give us something simplified is even though these were simplified, if we look at kind of going across like this numerator and this denominator, those aren't coprime to each other, right? They carry a common factor with each other. And because of that, when we combine everything, all those factors get combined into one numerator and one denominator, so that means it's not going to be coprime anymore. So what we basically need is for each numerator to be coprime with each denominator that we're working with here. Right? In this example, 1 is coprime with 3 and 1 was coprime with 2. Similarly, this one was coprime with 3 and 2. So that gave us a numerator that was produced by things that had no common factors with any of the stuff that was used to produce the denominator, which means that this is going to be a coprime numerator and denominator, which makes it simplified. So let's write down what we need. Each numerator must be coprime with each denominator. So for example, if we do 2/3 times 5/9, 2 is coprime with 3 and 9, 5 is coprime with 3 and 9, so this will give us a simplified fraction right off the bat when we multiply it, right? No common factors in 10 with 27 because they weren't produced by anything with common factors. But if I had something like 1/3 times 9/5, even though these are both simplified, because 3 and 9 have a common factor of a 3, that's going to be a common factor when we combine them. 1 times 9 is 9, 3 times 5 is 15. These can both be divided by 3, that common factor of that 3 and 9, right? So we get 3/5 here. Okay, so I hope you understand that, and that is the exercise video. I hope you found it useful. As always, I would love to hear your thoughts in the comments. And yeah, let me know some of the interesting things that you do with fraction multiplication, and I'm going to see you in that next video. But until then, you have a good one, you stay groovy, and I'll see you then.
F.O.A. Maths.